Usually when we think about our DNA, we picture this incredibly rigid, finalized blueprint, like a movie script that has already been printed, bound, and handed out to all the actors.
Right. Yeah. It's a comforting thought, honestly. You get what you get. The script is totally set, and, well, that's the end of the story.
Exactly. Your eye color, your height, your biological destiny, it's all just locked in from day one. But then, you look at your own body and suddenly that whole analogy just falls apart.
Oh, completely falls apart.
Because think about it. Your DNA is largely the exact same in every single cell of your body. So if the script is identical, why does a heart cell look and act completely differently than a brain cell?
Yeah, how does the heart cell know to beat right?
Right. While the brain cell knows how to, fire an electrical signal.
It really is a biological paradox when you first start to unpack it. And honestly, it's the perfect entry point into the concept we're exploring today, which just completely upends that rigid view of biology.
So welcome to today's deep dive. We are exploring the invisible layer of biology called epigenetics. Based on the comprehensive Wikipedia overview we're unpacking today, we're going to figure out how your body regulates, reads, and alters the expression of your genetic code.
Without actually changing a single letter of the underlying DNA sequence.
Exactly. We're going to see how your daily life alters your biology and ask the massive question: can you pass your life experiences down to your descendants?
The word itself actually gives away the secret. The Greek prefix epi means on top of or in addition to. So epigenetics is literally the science of what is happening on top of your genetics.
Okay, let's bring this back to that movie script analogy for a second. If your DNA sequence is the typed dialogue of the script, epigenetics is like the director's notes.
Right. Yeah.
It's the highlight or the crossed out lines, the margin doodles that dictate how the script is actually performed by the actors. The underlying words haven't changed at all, but the final performance is completely different.
I take that even further, actually. It's not just notes on the page. It's whether the actor is even allowed to open the script to a certain scene in the first place.
Oh, wow. Okay.
Yeah. So to understand how the environment changes our bodies, we really have to look under the hood at the physical mechanisms our cells use to actually highlight or cross out parts of that DNA script.
Right. So we're talking about chromatin remodeling. But before we get into the heavy weeds there, I'm picturing a microscopic construction zone. How does a cell actually restrict access to the script?
Well, think about the physical reality of DNA. It is incredibly long. If you took the DNA in just one of your microscopic cells and stretched it all the way out, it would be about 2 meters long.
Wait, 2 meters in one tiny cell?
Yep. 2 meters. So to even fit inside the cell nucleus has to be packed incredibly tight. It wraps around these spool-like proteins, which are called histones.
Okay, so if it's spooled up super tight, the cell's machinery just can't get in there to read the genes. The script is basically glued shut.
That is the default state, yeah. And this brings us to the first major epigenetic mechanism, which is histone modification.
Okay.
So when the cell needs to turn a gene on, say, a gene that tells a stomach cell to produce acid, it attaches a chemical tag to the tail of that histone spool. A really common one is an acetyl group.
So this acetylation process, does it physically change the spool itself?
It does. Adding that tag literally neutralizes the positive electrical charge on the histone protein. And because DNA has a negative charge, neutralizing the spool loosens its magnetic grip on the DNA.
Oh, that makes sense.
Right. So the DNA unwinds just a little bit, the gene is exposed, and the cellular machinery can finally get in there and read it.
Okay, so loosening the spool is the highlighter. It tells the cell, hey, read this part. So what's the black marker? How do we cross a line out so a skin cell doesn't accidentally start producing stomach acid?
That would be the second main mechanism, which is DNA methylation. Instead of modifying the spool, the cell adds a tiny chemical tag, a methyl group, directly to the DNA molecule itself.
Directly to the DNA.
Directly to it, especially at these places called CPG sites. Think of it as a molecular do not read sticker. When these stickers pile up at the starting block of a gene, they physically block the machinery trying to read it. The gene is silenced.
Got it. So a liver cell is a liver cell because it has do not read stickers plastered all over the brain cell instructions, but it has unwound and highlighted all the liver cell instructions.
It's exactly the core of cellular differentiation, yes.
Which brings up this historical concept we came across from the 1940s, the epigenetic landscape. It was proposed by this British embryologist, C.H. Waddington. I found this fascinating, but a little tricky to visualize.
Yeah, Waddington's epigenetic landscape is a super classic visualization in biology.
Right, so he described embryonic cells as marbles resting at the very top of a hill.
Imagine a hill with all these various valleys and branching pathways leading down.
Okay, yeah. So as the embryo develops, the marble starts rolling down the hill, and it falls into a specific valley. As it keeps rolling, the valley gets deeper, which restricts the marble's path more and more.
Until eventually, it reaches the bottom and is trapped in that one specific valley. It has irreversibly become a liver cell.
But what I don't quite get is, what physically stops the marble from just rolling back up the hill? Like, what keeps it trapped?
The walls of those valleys are physically built out of the epigenetic tags we just talked about. The methyl stickers and the tightened histones are the actual barriers preventing that marble from rolling up a ridge and suddenly turning into a heart cell.
So they lock the cell into its fate.
Exactly.
But if these tags are just physical stickers or tightened spools, how permanent are they really? Because our cells are constantly dividing and replacing themselves, right?
Right, all the time.
So if I cut my arm, my skin cells have to divide to heal it. When a skin cell splits in two, do the stickers just fall off? Does the new cell have to figure out its identity all over again?
That is a massive biological vulnerability you've just hit on. If they fell off, we'd literally dissolve into a chaotic mass of confused cells. So no, these epigenetic states are heritable during cell division.
Wait, heritable? Like the cell passes it down?
Yes. Your body employs these microscopic maintenance workers to copy the notes over.
How on earth does a maintenance worker copy a sticker onto a new cell?
Well, when your DNA replicates during cell division, the zipper-like structure splits straight down the middle. So now you have a half-old strand and a newly forming half.
Okay, I'm with you.
The new half obviously doesn't have the do not read stickers yet. But a specific maintenance enzyme like DNMT1 patrols this newly forming DNA. When it sees a metal sticker on the old half of the zipper, it immediately slaps the exact same sticker onto the matching spot on the new half.
So it's literally a tiny biological copy machine for the director's notes.
Exactly. It ensures the epigenetic memory is perfectly preserved, so a dividing liver cell produces another liver cell every single time.
That is just a brilliant piece of biological engineering. So, okay, we understand the machinery now. We know how the cells restrict and allow access to the script. But here is the pivot.
Right.
If the machinery is so good at maintaining the status quo, what causes these instructions to change over a person's lifetime? Because for you, the person listening to this right now, your daily choices are actively editing this script.
We're moving from the tightly controlled environment of embryonic development to the completely chaotic reality of living in the world. Your environment is constantly writing on your genome.
And I think the most striking proof of this comes from studying identical twins.
Oh, twin studies are absolutely the gold standard here. Identical twins come from the exact same fertilized egg. They share the exact same underlying DNA script.
Right.
And when researchers look at them in early childhood, they're practically indistinguishable on an epigenetic level too. Their methyl tags and histone modifications are perfectly in sync.
But as they age, that synchronicity starts to fracture, doesn't it?
It does, massively. As they grow up, maybe one twin moves to a super polluted city while the other stays in the countryside. One eats a highly processed diet, the other doesn't. One has a traumatic medical history, the other remains healthy.
So their lives diverge.
And over decades, their epigenomes begin to wildly diverge right along with them. This phenomenon is known as epigenetic drift.
So by the time these twins are, say, in their 70s, their DNA sequences are still completely identical, but their epigenomes look like they belong to totally different people.
Exactly. You'll see one twin who has accidentally plastered a do not read sticker over a gene that protects against tumors, while the other twin still has that protective gene fully active.
This drift concept basically perfectly explains the difference between our chronological age, the number of candles on your birthday cake, and our biological age, which is how battered and worn down our actual cells are.
Spot on. And to understand why this drift happens, we really have to look at the staggering amount of microscopic damage our bodies endure every single day.
Okay, this part of the research genuinely surprised me. I always thought of DNA damage as something that happens when you get an X-ray or sit out in the sun way too long.
I mean, those certainly cause damage, but your own normal cellular metabolism is actually the biggest culprit.
Really? Just normal metabolism?
Yeah. The simple act of converting food into energy inside your cells creates biological exhaust, specifically oxidative stress. And this exhaust physically damages the rungs of your DNA ladder constantly.
Constantly? Like how often?
We're talking about roughly 60,000 microscopic breaks and lesions in a single cell every single day.
Wait, 60,000 times? Just from keeping me alive?
Just from keeping you alive. It forms specific oxidative damage markers like 8-OHDG all over the place.
Okay, so my cells are taking heavy fire just from existing, but obviously my body fixes this, right? Otherwise, I wouldn't have made it to my second birthday.
Yes, your cells have an incredible repair crew. They patrol the DNA, cut out the damaged sections, and patch them back up. But here is the critical flaw in the whole system.
Okay, brace me.
The very act of repairing the physical DNA can accidentally, permanently alter your epigenetic markers.
Why? Does the repair crew mess up the notes while they're fixing the break?
Essentially, yes. When a repair enzyme spots a pothole in the DNA, it binds to it to fix it. But to do its job, it often recruits other specialized enzymes whose whole purpose is to strip away methyl groups.
Oh, no.
Yeah. So in the chaotic process of patching the physical pothole, the repair crew accidentally scrapes off the "Do Not Read" sticker that was sitting right next to it. They call it demethylation.
Wait, so the pothole is fixed, the DNA sequence is completely whole again, but the director's note is just gone.
Poof, gone. And the gene expression is permanently changed. A gene that was supposed to be completely silenced in that cell might suddenly get turned on because its restrictive sticker was collateral damage during a routine repair.
And if you multiply that tiny error by 60,000 repairs a day, over decades,
Yeah.
I mean, you easily see how the simple act of living and aging literally rewrites your biology.
It leaves these permanent epigenetic scars.
But we aren't completely helpless against this wear and tear, right? The research indicates that what we put into our bodies can act as a sort of shield. Like, diet plays a massive role in protecting these tags.
It does. Specific nutrients provide the exact chemical building blocks that your epigenetic machinery needs to function properly.
Like, they found that consuming soy isoflavones or the anthocyanins from bilberry extract, basically compounds found in specific plants and berries, can visibly reduce this oxidative DNA damage.
Exactly. You are feeding your cells the tools they need to neutralize that biological exhaust before it creates a pothole in the first place.
Right. And by reducing the number of potholes, you reduce the number of times the repair crew has to go in, which directly prevents those accidental epigenetic scars.
It's all connected.
Let me push back on this a bit, though. Let's say I don't eat perfectly. I accumulate these epigenetic scars over the years. My stickers get scraped off. My spools get tightened in the wrong places. Is this ultimately what disease is? Are we just talking about wrinkles and aging, or are we talking about the root cause of major illnesses?
Oh, we are talking about the root cause of major illnesses.
Wow.
And this realization has caused a massive paradigm shift in how we view diseases, particularly cancer.
Yeah.
Well, for a long time, the medical community viewed cancer almost strictly as a genetic disease, meaning a physical mutation or a literal break in the core DNA sequence.
But if a cell just loses its epigenetic tags, you don't even need a physical mutation to get a tumor.
Think about how a cell controls its own growth. It has genes designed to hit the brakes and trigger a self-destruct sequence if the cell starts behaving erratically.
Okay.
If the repair crew accidentally slaps a "Do Not Read" sticker over that specific brake pedal gene.
Then the cell never reads the instruction to stop dividing. It just multiplies endlessly. The DNA sequence is perfectly fine, but the epigenetic notes are telling it to become a tumor.
Exactly.
Yeah.
Cancer is now recognized as both a genetic and an epigenetic disease. The malignant growth is heavily driven by these abnormal chemical tags.
But there's a huge silver lining here, right? Because unlike a genetic mutation, where the underlying code is physically broken or just missing, an epigenetic tag is literally just a sticker. It can be removed.
That is the most promising part of this entire field. Epigenetic changes are theoretically completely reversible.
Wow.
You can't easily go in and rewrite a corrupted DNA sequence in a living patient, but you can chemically coax a cell into adding or removing a tag. This has led to an entirely new class of FDA-approved epigenetic medicines.
Things like DNMT inhibitors and HDAC inhibitors,
Yes.
right? So instead of just poisoning the cancer cells with traditional chemotherapy, these drugs are designed to go in and essentially do an epigenetic reset.
They target the specific enzymes that control the tags. If a cancer cell has used "Do Not Read" stickers to turn off its self-destruct mechanisms, these new drugs sweep in, chemically strip away those specific stickers, and suddenly the cancer cell remembers it's supposed to self-destruct.
It restores normal gene expression.
Precisely.
The idea that we can medicate the director's notes is just wild to me. But I want to take a hard left turn here because everything we've talked about so far is very physical toxins, diet, physical cell damage. Let's connect this to the brain and the totally abstract world of the mind. how does the brain use epigenetics to deal with abstract concepts? Like, how do you remember a phone number or a frightening event?
This is perhaps one of the most mind-bending applications of epigenetics. We tend to think of memories as purely electrical, just, sparks flying around a neural network.
Right, synapses firing.
But forming a long-term memory is fundamentally a structural epigenetic process.
Let's break down the mechanics of this, because the rat study we looked at sounds like pure science fiction.
Researchers were looking at rats undergoing fear conditioning, basically teaching them to associate a specific environment with a mild foot shock. They wanted to see what was actually happening in the brain cells when a strong traumatic memory is formed.
And what they found completely upends the idea of memory just being an electrical spark.
Completely. They discovered that when the brain creates a powerful new memory, it actually intentionally breaks the DNA inside the neurons of the hippocampus.
Wait, I need to make sure I'm hearing this right. To form a memory, your brain intentionally causes double-strand breaks in its own DNA. The very thing we just said, the cell spends all day trying to prevent and repair.
Yes. Specialized enzymes purposely snap the DNA strands in over 100 different locations.
But why? If I'm trying to remember to avoid a dangerous situation, why is my brain ripping its own script apart? Let's use the script analogy. Is the director literally tearing the pages in half?
It's exactly like tearing the pages out so you can read them faster. Remember how tightly schooled the DNA is around those histones?
Yeah.
When you experience something really intense, the brain needs to immediately access specific early response genes, like EGR1, to physically build new connections and lock in that memory.
Okay.
Unspooling the DNA normally just takes way too long. Breaking the DNA rapidly relieves the physical tension, allowing the chromatin to just spring open instantly.
Oh, wow. So the brain literally breaks the DNA to speed read the script. What happens next?
Once it's sprung open, the cell rapidly strips away the methyl stickers on those specific genes. This sudden access allows the neuron to pump out a massive wave of new instructions in the form of messenger RNAs.
Right.
These instructions are packaged into little molecular cargo ships, neuronal granules, and transported all the way down the dendrites to the synapses.
Where they physically rebuild the connections between the brain cells. So a memory isn't just a spark. It is a physical remodeling of the brain, driven by an intentional epigenetic rewiring.
The psychological experience literally becomes physical biology.
Okay, if my life experiences and my memories are fundamentally altering my epigenome, we have to tackle the massive elephant in the room, transgenerational inheritance. Can I pass these life-altered tags onto my kids?
We are now entering the most fiercely debated territory in modern biology. For over a century, the absolute unbroken rule of genetics was something called the Weismann barrier.
Which basically says that the life choices I make only affect me. If I spend 5 years eating terribly and acquiring all these epigenetic scars, I was taught in high school biology that only my core DNA goes into my sperm or eggs, not my life choices.
Right, the biological firewall. It dictates that traits you acquire during your lifetime cannot be passed to your offspring. Only the pristine DNA sequence gets passed down.
And when that sperm and egg meet, all the epigenetic tags are supposedly wiped completely clean. A total factory reset.
Exactly. The embryo starts with a totally fresh script, but population data has really started to show massive, unexplainable cracks in this barrier.
Let's talk about the Epigenetics study, because this data suggests human trauma might actually echo across generations.
Epigenetics is a remote, highly isolated village in northern Sweden. Because of its extreme isolation and really harsh winters, researchers were able to track meticulous historical records of harvests and extreme food availability during the 19th century.
So they knew exactly when there were feasts and when there were freezing famines.
Yes. They then cross-referenced that feast or famine data with the detailed medical histories of the villagers' descendants decades later.
So they were looking at kids whose parents or grandparents went through severe starvation.
And the results were completely counterintuitive to the Weismann barrier. They found that the paternal grandsons, so the sons of men who were exposed to famine just before they hit puberty, were actually less likely to die of cardiovascular disease.
Wait, so the trauma of starvation in the grandfather somehow conferred a protective health benefit to the grandson. That implies the biological memory of the famine completely bypassed the firewall.
It strongly suggests it, yeah.
Yeah.
And the effect was incredibly specific. If the grandfather lived through periods of massive food surplus, the grandchildren actually had increased diabetes mortality.
And didn't it affect the women differently?
It did. The timing mattered tremendously. For women, the granddaughters of women who experienced famine while they were still in the womb meaning the famine occurred while their own primitive egg cells were developing, ended up having shorter lifespans on average.
So we have this sweeping epidemiological data in humans. But human lives are incredibly messy. There are a million variables. To really prove this, you'd need to control the environment perfectly. Which brings us to the highly controversial mice study.
Yeah, we have to navigate this carefully as it sits at the absolute center of a fiery scientific debate. It's a prime example of science wrestling at the very frontier.
Right. And to be clear, we are just looking at what the sources say here. We aren't taking a side. So here was the setup. Researchers took male mice and trained them to fear the smell of cherry blossoms.
Right.
They did this by pumping in the cherry blossom odor and simultaneously giving the mice a mild foot shock. Over time, the mice became terrified of the scent alone. Then, those male mice bred and had offspring.
And according to the published paper, those offspring who had never been exposed to the foot shock and had never smelled cherry blossoms before exhibited an innate increased fear response when they were finally exposed to the odor.
They somehow inherited the specific fear.
The authors proposed that the terrifying experience caused an epigenetic change in a very specific gene, the M71 gene, which governs the odor receptor for cherry blossoms in the nose.
And crucially, they claimed this altered epigenetic tag survived the factory reset in the sperm and was passed down to the next generation.
Now, to be strictly impartial here, we have to look at the massive waves of criticism this study received. You can't just claim the firewall is broken without intense scrutiny.
Oh, definitely. Critics totally tore into the statistical analysis. They pointed out that the probability of these specific results being perfectly replicable exactly as reported was impossibly low, something around 0.4%.
They basically said the math was way too clean to be real.
Right. They argued the study lacked statistical power. And a major criticism was that the researchers didn't properly track which offspring mice were siblings.
Which is a huge deal. In biological studies, if you treat a bunch of siblings as statistically independent variables, you ignore genetic clustering. That can severely skew the data and create false positives.
But on the other side of the aisle, the original authors completely stood their ground. They published rebuttals defending their methodology.
They pointed out that the critics had omitted certain negative results in their probability calculations, which made the data look artificially clean in the critique.
Though they did concede they would track sibling mice more rigorously in future studies, so it's basically a stalemate right now.
It is. The mechanical explanation for how a specific learned fear of cherry blossoms could travel from the brain, bypass the Weismann barrier, and selectively alter a single odor gene in a sperm cell remains entirely unexplained. The scientific community simply does not have a definitive answer yet.
So what does this all mean for you, the listener? If we step back from the specific enzymes and the controversial mice, the core message of this deep dive is profoundly empowering.
It really is.
You are not just a static printout of your DNA sequence. You are a dynamic, living document. Your script is constantly being highlighted, annotated, and rewritten by your environment, your meals, your aging process, and even the memories you physically build in your brain.
It's a beautiful, incredibly complex view of human biology. But we have an obligation to ground that beauty in reality. Because the science of epigenetics is still in its infancy, it has unfortunately been heavily co-opted by pseudoscience.
Oh, the quack authors. The internet is just full of them.
It is everywhere. Scientists explicitly warn against the sensationalism spreading in public media. There are authors and influencers making completely unfounded claims that you can magically manipulate your genes, heal any terminal disease, or overwrite your biological reality purely through mind control, meditation, or positive thinking.
Right. The science says that eating a diet rich in certain plants might provide the tools to help prevent an epigenetic scar from oxidative damage. But that absolutely does not mean you can manifest your way out of a severe genetic mutation.
Exactly. Misuse of the scientific terminology creates dangerous, predatory misinformation. Epigenetics is a breathtaking biological mechanism of chemistry and physics. It is not magic.
Which leaves us with a fascinating, provocative thought for you to mull over. We know our choices matter. We know our environment is holding the director's pen and actively shaping our biology.
That much is clear.
But where exactly is the boundary? Where is the line between the empowering scientific truth that our lifestyle impacts our epigenome and the dangerous pseudoscientific illusion that we have complete magical control over our biological destiny?
It might genuinely be the most important philosophical question in modern biology. How much of the script can we actually rewrite before the ink dries?
Next time you look in the mirror, remember, The script may be printed, but the director is always taking notes. And until next time, keep diving deep.